Okay, so welcome everybody. Welcome to the CS560 algorithms and their analysis. So this is the first class of this semester, of this spring semester, and hope everybody can have a very fresh start. Okay, so basically today we're gonna have a very overall introduction to the course, to the content, the structure, the way of delivery, and details like office hours, assignments, grading policies. We can discuss that in this Zoom session. And I'm going to video record everything. So what you we will be talking about will be recorded, and probably later I will upload the video to my personal YouTube channel, and that will YouTube can generate closed captions automatically, which is nice. And actually, I tried Zoom link, the Zoom Cloud video, recording, but the resolution is not that good compared to YouTube. So I'm going to stick with YouTube. So for your convenience to watch the video lectures anytime after the Zoom session, after this Zoom session is ended. So I will post the video links to Canvas. The way that I was used to do is to create a page for, first of all, in the module section on Canvas, I will create a module based on the topics that we are covering. Say we're covering sorting algorithms, then there will be a module named sorting algorithms on Canvas, and I will put the recorded video lecture, the quiz questions, the assignments, and if there are any discussion in the office hour, then I can probably also upload that discussion part, that recorded videos for the discussion part to the same module, right? So yeah, so all the organization of all the course contents are pretty modularized. Okay, and this is the second time that I taught this class using Canvas. And before that, we SDSU uses the Blackboard, which I think Canvas is a much better option, and it allows very clear organization of the modularized course contents. Yeah. All right. So something about this course. Okay. So the title, the name is algorithms and their analysis. So we emphasize analysis. So it's basically not a programming-based course. We don't, so all the assignments are not program-based tasks, okay? So it's an analytical course. So basically the learning goal of this course is to understand different types of algorithms, or we say different families of algorithms. Okay, see, we based on the structure of the textbooks we use, we can categorize algorithms into different families. Okay, like divide and conquer, greedy, graph, dynamic programming, and so on. So within each category, there are various types and multiple sub problems, or very specific smaller algorithms, small problems that we're going to cover in that category. Okay, so the goal is to understand the techniques that we can use to analyze the algorithms. That's in terms of the running time, the memory costs of running specific algorithms. Okay, we will learn the mathematical notations that are necessary to carry out the analysis. Okay, but also it's computer science class. So even though we are not going to write programs using any specific programming languages, say Python, Java, C. No, we are not going to use any specific program languages, but we are going to use pseudocode, okay, to implement algorithms or to. So first of all, we need to be able to read the pseudocode and understand what the functions of a piece of pseudocode is. And then in most of the assignments and exam questions, we will have questions that ask you to implement certain algorithms, use the pseudocode. And this type of pseudocode is have the same conventions that we will use across this whole course. So we will have very consistent grammars defined for this specific type of pseudocode. Okay. So the last learning goal is that we want to have a very we want you to learn something that is very flexible and useful. Say, given a very concrete problem in the real world, and then you will be able to know how we deal with, how we solve those problems using algorithms. And we also need to be aware that even though there are multiple possible solutions, we can compare the efficiency. We can compare which one is better, which one runs faster, which one may leave you wait forever. So these are the overall learning goals of this course. Okay, so the prerequisites are basically the so I think here there's a typo. It shouldn't be linear algebra. It should be the discrete math and data structures. Okay, so in the next few slides, I think we're gonna let me grab the textbook. I'm gonna introduce the textbook and some other stuff. Okay. So far, any questions on this slide? All right. Okay. Okay. So textbook is by Corman and Lyserson, CLRS, with basically these four people, CLRS, professors from MIT, I think, yeah. And this is a, oh, maybe you cannot see this. Let me turn off the virtual background. Okay. All right, can see this. This is how the cover looks like. So the third edition is the latest edition, I think. There shouldn't be any more later editions for now. All right, third edition. So you don't need to buy this. So I will suggest you to use the link in the syllabus to download the PDF copy of it. So it's a very long book. Will the second edition work? I don't know. There are some chapters missing and modified since the second edition. So ideally, you need to use the third edition, right? But if you have the paper-based book for the second edition, that's okay, because we have a download link anyway for the third edition. Okay, you can use this link to download the textbook. And
excuse me, Professor, where is that link in the Canvas?
so it's on the syllabus. So if you syllabus column or syllabus page, so if you enter the course page on the left navigation bar, you will see a syllabus.
Yeah, textbook
button.
link.
Yeah,
Yeah, I saw it. Thank you. Sorry.
yeah. So,
Excuse me, Professor, I have a question.
yeah.
Will the slides be available to us on Canvas?
Yes. So today I didn't upload the Canvas, the PDF yet, but in the following, in all the future lectures, I will upload the slides before the lecture, before the Zoom session starts. Okay, so that you can open it in your laptop or print it out.
Oh, I have a question.
Yeah.
Are you gonna have a more detailed schedule? Because on the syllabus it just says when it's released, but it doesn't really have like a due date, like for most of these assignments.
Mm-hmm. So for the specific due dates of the assignments, right? Is that what you are talking about? Yeah. So I used to do that, and in the last fall semester, we have 4 assignments. That is 4 question sets in total, and I want to make some changes. I want to split the 4 assignments into 8 smaller ones. So that means I need to adjust all the due dates correspondingly. So for that part, I'm not done with all the schedules yet. So I will do that over the weekend, and hopefully before we start the first lecture, then we will already, we will have those deadlines already posted.
Okay, thank you.
Yeah, I'm going to do that. Okay. All right. So all the lectures will be, the slides will be provided, and I think that is pretty much sufficient to cover all the topics. Okay. But reading the textbook, like the full chapter would be very helpful to understand the details, because in the slides, I'm not going to cover everything that is that shows in a textbook. Okay. So basically, this is a very good book that's worth reading. Okay. All right. So yeah, let's go back. We have mentioned this. We don't have any requirements on specific programming languages. Okay. And all the assignments and exams are paper-based. Okay. But that doesn't mean you the paper-based questions can be of various types. Like you can have, we would have like mathematical proof, that you need to use mathematical induction to prove some theorems, or you can you will use you will need to read the pseudocode and to specify the places that could be wrong, and also make the changes where corrections need to be made, like that. So even though it's all the questions are paper-based, you will still need to read some pseudocode and to write some pseudocode to implement algorithms. All right. So print and scan, yeah, that's basically what we do. So another thing, prints and scan, that's a good point. Thank you for mentioning that. All the assignments will be released, will be published in a PDF file. So you need to have a paper to work on that assignment questions, and you need to write down all the necessary steps and the answer on your own paper, and then make a scan or take a photo of your answers to the assignment questions. And I would prefer you to create a one Word documents or PDF documents to include all your scans. Okay, if you submit everything into several image files, JPEG files, that'll be much harder for our TA to grade your work. Okay, so for the exams, we will mention that later. We will have 2 midterm exams and the final exam, and all the exam questions will also be paper-based. So that means you need to print it out. You need to print the questions out. But for the exams, I don't think you need to use additional papers, because when I design the questions, I leave sufficient space for you to fill out the questions, to fill out the answers. All right. Okay. So yeah, and something about myself. So my name is Yang Xu, and I am an assistant professor of computer science here in SDSU. And my research areas include natural language processing, basically using machine learning methods to study, to understand the human language and to build, to write algorithms, write computer programs that understand human language. Okay. And if you're interested, you're welcome to visit our lab's websites. And also, if you have interest in doing research projects with me, you're more than welcome to contact me by email. Wait, I didn't include my email here. Okay, so you can find my email address on Canvas anyway. All right, so I think that's all I want to mention before we start the introduction part. That's already an introduction, actually. So I think I want to go to the last page. Okay. I quit the view mode of points and let me go to the last page and share the screen again. So here we'll talk about grading policy. Okay, so here this slide is not changed yet. So the assignments takes 40%, right? And I said 4 assignments in total. So that's the old plan that I wish to change, and I want to split each big question set into smaller ones. I want to have 8 assignments more, so that they spread more. They are more spread across the whole semester. Okay, but that total proportion doesn't change. That's 40% from assignments, and we will have 2 midterm exams, and each take 15%. Okay, and in the midterm, there will be 5 to 6 questions, paper-based questions. Okay, 90 minutes for each midterm, and the final will take up to take 20%. Okay, and there will be more questions. Okay, so in terms of the scope of the questions, so the midterm 1 and the midterm 2, they don't overlap. Okay, they cover different sections. Okay, so the final exam will also will not cover the previous contents in midterm. So the coverage of the final exam is not the whole course, but we basically cover the whole course contents like incrementally. Like maybe midterm exam covers the first 1/3 or less, right? The second midterm covers the mid 1/3, and the final exam covers the remaining parts. Okay, so there's no overlap between those final exams. Okay, so the third part is the quiz questions. Okay, so the quiz question, the goal is basically to see if you have watched the if you joined the session, and if you didn't join the session, that's okay. So I'm not going to test the counted attendance explicitly during the session, during the Zoom session, but I will have quiz questions that require you to answer. And in order to get that correct, you basically need to watch the video lectures if you cannot join the Zoom meeting. Okay. So that is the grading policy. Any questions on that? I have some more chats. Okay.
I have one.
Yes.
So for the in-lecture quizzes, I would assume that's right after a class, right?
Yes, yes. That's right after. That will be published after the session, the lecture is over. But I will have 1 or 2 days deadlines later.
Okay, gotcha. Thank you.
Yeah, it's not like immediately due, something like that. Okay, any questions in Zoom? Yeah, quiz will be due maybe 2 days later after the class date. Okay. More questions. Okay, good. Let me go back to where I stopped. Oh, nice. So yeah, let's start this first lecture for the introduction of algorithms and their analysis. Okay. So, yeah, some more questions. What if an R&R day follows a lecture day? How would you give time for the quizzes? So the quiz questions will be, it's basically not that intellectually challenging, and that is easy to, I would say, compared to the assignment questions, the quiz ones will be easier to deal with. So it's basically after you have watched the lecture, you should be able to answer the quiz questions quite easily. Okay, but as I said, the purpose of those quiz is to make sure that you have watched the lectures, you have gone through the lectures at least once. Old lectures, yeah, that question I said earlier. So I will upload the videos to YouTube and post the YouTube link to the Canvas page. Okay. All right, so let's start talking about algorithms. So it's a quite exciting concept, and when we talk about the term, different people have different ideas in their mind, and as a computer science students, we have seen this term with much more chances than others. So in this textbook, we will find a pretty clear definition that an algorithm is a procedure. It is a computational procedure. And that procedure will do something based on the inputs, okay? And it will take some inputs and produces some value as outputs. So this is what this procedure does, okay? It's defined by the inputs and the outputs, okay? And it is a tool to solve computational problem, okay? So once an algorithm is defined, given an inputs, if the input doesn't change, then the output should also remain the same. It shouldn't be vary due to unknown reasons. Well, unless there's some randomness involved in the algorithm. Okay, so that is a special case. But in most of the cases that we will talk about in this lecture is that once the algorithm is defined and that it correctly works, then given the inputs, it should always, given the fixed input, it should always generate the fixed outputs. Okay. So we can use this input to output mapping relationship to basically define any type of computational problems. Okay. So for example, we will talk about a simple sorting algorithm. Given a input sequence that is unsorted, and we hope that the algorithm can correctly sort the inputs, whether in ascending order or descending order, the outputs will be fixed given an input sequence. Okay. So once the relationship, the problem is defined by the input to output relationship, then the algorithm simply describes a specific procedure or a set of steps that are needed to achieve this input to output relationship, mapping relationship. Okay. So let's look at a very classical sorting problem as example. And to a sorting problem, the input is always a sequence of numbers. Okay, so given n numbers, and from A1 to AN, so this A can be integer numbers or floating numbers or whatever numbers that can be sorted. Then the output is also defined. It's defined as a permutation. In other words, it's a reordering of the original input sequence. Okay, but in the output, in the permutation, all the elements needs to satisfy some constraints. So the A1 prime should be smaller than A2 prime, and so on. So that is the most typical ascending sorting algorithm, what ascending algorithm does. Okay, say given the integer numbers like this, 31, 41, 59, and the output should always, if the algorithm works correctly, you should always generate the same sorted order sequence, which is from the smallest element to the largest element. Okay, so I have 3 arrows in the middle, which means that there are multiple ways to implement the procedure that maps the let me see, maps the left half input to the right half output. Okay, so when we look at an algorithm, we usually care about, first of all, it should be correct, right? We want our desired outputs. So if given the unsorted order and there's an error, and the returned output is not sorted, or there's errors in it, then that's not something we want, right? So the algorithms usually need to be first, it needs to be correct. And after that, we can consider other more advanced components, more advanced attributes. Like we want the algorithm to run fast. We want sometimes we want it to run fast, and more importantly, we maybe want to use less memory space. Okay, but that's very different circumstances that we need to consider, depending on what constraint we have. Right? If we are constrained by time, then we prefer more timely efficient. But if we have a sufficient amount of time, but we don't have enough memory space, then we will prefer something that is more efficient in memory cost. Okay. All right. That's the sorting algorithm as an example to introduce the concept of algorithm. Okay. So yeah, let's see the correctness. Okay. So when we talk about correctness, that's something we want, right? So usually speaking, we want to avoid any algorithm that generates the wrong outputs. Okay, so the correctness in this course, first of all, it is important, but it is not the core of analysis in this course. Okay, so we will basically, given an algorithm, we will examine the correctness of this algorithm using examples, using simple examples. But a more strict analysis of correctness requires some very formal ways to analyze the invariance in the algorithm. So, for example, in a sorting algorithm, as an example, whenever a sort happens, there's usually some code structure like loops, like for loops or while loops involved in the sorting algorithm, right? So in order to formally prove that this loop is correct, we need to use the technique called loop invariant to prove the correctness. But as I said, this is not the core of analysis for this course. So in order to show that the correctness of the algorithm, we will basically use simpler examples and plus some intuition. Okay, so as long as the jigsaw pieces connects in our mind model, and when we realize that this algorithm is correct, then we will not use the formal ways to strictly prove the correctness. Okay, so sometimes an incorrect algorithm, like given an input, it doesn't generate the desired outputs, then that is usually what we don't want. But sometimes it can be useful, right? Because not all the algorithms, not all the problems can have a very efficient algorithm to get a solution. So that's very unfortunate. So a lot of the problems in the real world are really hard problems that we don't even know whether an efficient algorithm exists. So in some of those cases, if we cannot find an 100% accurate algorithm that solves the problem correctly, then we can take a step back. Say, maybe we can use something that we know is incorrect, but the error rate can be controlled. And the advantage is that use that incorrect algorithm, we have a much more speed up efficiency. It runs really quick. So sometimes we can do that trade-off. Okay, depends on at what scale we are talking about the problem. Okay. All right, that's the correctness. So in this course, we will primarily focus on correct algorithms. Okay, so incorrect algorithms can sometimes be tolerable, but we basically focus on the correct algorithms, and then we deep into those, go deep into the correct algorithms and try to find the better ones among the correct algorithms. So I see a question: would you consider greedy algorithms to be incorrect algorithms? That is a very good point. So I would say, so first of all, the greedy algorithms, the basic idea of greedy algorithm is that it's usually a iterative algorithm. And by iterative, we mean that we are starting from some point and we want to approach a maximum point, or we want to approach an optimal solution. But within that iterations, we don't know whether our current step is will for sure lead to the ultimate, will for sure lead to the optimal goal. Okay, we don't know whether our current step is the globally best option or best step to go, but we can assume that. So the greedy algorithm assumes that if we take the locally best algorithm, so we take the step that seems correct at a current step, then it will lead us to the global optimal solution. Okay, so but when we are designing the greedy algorithms, we don't know whether this is the correct or incorrect algorithm. We will only test the correctness of the algorithm based on examples. Okay, so, and the textbook, I think in the chapter for greedy algorithm, it provides some formal ways to analyze, to prove the correctness of greedy algorithms. But I think that mathematical techniques involved in those formal proof are beyond the scope of this algorithm, of this course. So in the greedy algorithm chapter, we will show that, at least we'll show some examples about why the currently local step will lead to locally best step will lead to the globally optimal solutions, and we will see their constraints in those greedy steps. If the constraint is changed, if the problem is changed, then probably the current best step is not necessarily the globally optimal solutions. Okay, so yeah, I think it's a good point, and it brings some topics in advance. Okay, so now let's see what kind of problems can be solved by algorithms. So I list in the next few slides, I will list a couple of real-world examples. So, for example, the Human Genome Project, which is to identify the human genes, the genes in human DNAs. So in those computational tasks that involves the sequence of genes, there are a lot of needs to determine the similarity between sequences, or to find how much similarity are there between pairs of genes, pairs of DNA segments, and those, because there are millions of hundreds of thousands of genes available in human DNA. That is a very computationally costly tasks. Say it's not an easy task, even for simple tasks like to compare the similarity between two pieces. So we'll see a problem involves like that is related to this gene computation in the dynamic programming chapter, that we want to find the longest common subsequences between two segments, okay, which is a very classical example showing that how a good algorithm will solve the same problem with much higher efficiency. Okay, and second example, internet. We are now so used to the accessibility of data from the internet, okay, and we often overlooked the underlying algorithms that help us to transfer data among routers among servers to our clients through massive to transfer massive volume of data so quickly and accurately. Okay, so there's actually a very sophisticated routing algorithms involved, which is we will introduce some of the ideas in the graph algorithms part, because a lot of the routing task is to try to find the shortest path among on a very complex map, right? We want to reach our destination as quickly as possible. Okay, so that is routing, right? And for search engine, so it tries to find the relevant pages as fast as possible as well, right? So, but how the relevance of pages are estimated quickly, and how the pages are ranked in the first of all relevance, and in the really fast style. So those are all the functions handled by the efficient algorithms, underlying algorithms. Okay. Okay, and the third example, we have cryptography algorithms. I think it's coming to more popular topics recently as the cryptocurrencies, right? So it is actually the cryptography algorithms or digital signature algorithms that is behind the cryptocurrencies that basically solves the de-identification, okay, problems. So you basically use a pair of keys to secure your data. You keep the private key, which you can use to sign any piece of data. And after you sign the public, after you sign a piece of data, that data will be kind of engraved with the signature, and you can present the signature together with the public key to anybody else, so that someone else can basically evaluate whether this signature is generated by you. Okay, so that is a way to ensure the security computation with cryptography algorithms. So this is a rising field, and I think it'll be the tide will be up there at least for a long period of time in the future. Okay. Yeah, blockchain and cryptocurrency, as I mentioned, this is the future techniques. Actually, they exist quite a long time ago in history, but now it's a time that's more and more traditional centralized systems are going to shifting towards those techniques that is designed under this decentralized design ideologies. Okay. So we will have some, after these slides, we have basically introduced the real world problems that can be solved by different types of algorithms. Then let's look at some examples of algorithms, which we will cover in this course. So the first one, shortest path problem. Okay, so it's a problem that we are kind of using every day, like to find the shortest path between the source and the destination on the map. Okay, so this kind of problem is a very difficult one, and we basically need to carefully design an algorithm to solve them properly and correctly and efficiently. Okay, so this shortest path problem, we will cover it in the graph algorithms chapter, okay, which will be in the second half of the semester. And the longest common subsequence problem. So this is something we talk about when we will use when we talk about the human gene projects, that if we want to compare how similar two sequences are, then we will use a efficient implementation of such an algorithm. Okay, so typically a dynamic programming approach need to be used, which we will introduce during the mid semester. Okay, and topological sorts. Okay, that's another graph algorithms. Okay, so it's actually a quite commonly quite commonly used algorithm that basically any kind of software engineer projects need to rely on. So it helps to define the dependency relationships between software packages. Okay, so given a library of parts, it will figure out which part depend on which one. Okay, and it will list all the parts in such an order that the ancestors need to appear before the descendants. Okay, so that is a very important clarification work that we need to figure out in order to install a software correctly, or to figure out the correct interdependency relationships within a very complex software engineering projects. Okay, so that parts we will cover also in the graph algorithms. Okay, so the last example I use here is a convex hull problem. So this is an interesting example that you can find in the textbook, and it's not. I think we're not going to cover it explicitly in the book, in the slides, but it's an iterative problem that can be solved by figure out some clever strategies in each step. Like it's kind of related to the greedy algorithms. Okay, so given a endpoints on the plane, and the convex hull of those points is the smallest convex polygon that contains all the points. Okay, so and it's also have very significant practical usage, like on a map given several pinpoints, and you want to find those pinpoints on the region, and you can select as few points as possible to cover the biggest region. So these are all the algorithms or the computational problems that we often come across in real life. Okay. All right. So it's 2:48. I think if we cannot cover all the slides today, I think at least we need to cover this example. So it's helps answer this question. Can be answered by the examples that I'm going to show later here on this slide. So why do we need to study algorithms? So we all have a feeling that, or have a seems to be a common sense that computers are getting more and more powerful nowadays, right? We have super fast CPUs, we have super fancy GPUs that supports vector computation, that supports very good parallel computation functions, right? But even though we are having very powerful hardware, then why do we still need to study algorithms to improve the performance from the software perspective? Okay, because to answer that simply, with a simple sentence, computers are not infinitely fast. There's always a physical limitation there, which if we do not consider the algorithms at all, then it's a waste. It will be a waste to run a poorly designed algorithm on on a very fast modern computer. Okay, and also that's from the speed perspective. If it's from the memory cost perspective, memory are also some resource. It's not a free resource. It has its own limits. Okay, so the computation time and the memory, they are bounded resources, and bounded resources need to be managed scientifically, need to be managed correctly, and we don't want to spend all the resources. We want to put all the resources to solve the problem in an efficient way, without a waste of time and memory. Okay, so we'll look at an example to show. Okay, to solve one problem, if we have a good algorithm versus a bad algorithm, how much difference there can be given the different designs of the algorithms. Okay, so we'll compare two sorting algorithms. One of them is called insertion sort. Okay, and we assume, so this is just a mental experiment, we don't have specific numbers. We can assume that the insertion sort, it will take C1 times n squared instructions. So the instructions here means CPU instructions. So one CPU instruction is the primitive operation done by the CPU, which can be used to estimate how much cost a CPU, how much cost will be placed to a CPU computation. Okay, so it's a metric of resource cost. So the second algorithm we compare with is the merge sort algorithm. It will take C2 times n times logarithm of n, that much instructions to sort n items. Okay, so we are comparing these two items. All right, and we have C1 and C2, right? These are constants, and we don't know the concrete values yet. Okay, but we can make even bolder comparison. Say we assume that C1 is smaller than C2, which means the insertion sorts will have smaller cost. Okay, say we run the insertion sort on a faster computer. Okay, so that the C1 is smaller. Say, and we also we assume that it can execute, that fast computer can execute 10 billion instructions per second, which is fantastic. And also the low level, we also implement the insertion sort with some very quick program languages, which means the constant C1 is very small. Okay, so that's the advantage we give to insertion sort. And also we give some disadvantage to the merge sort. Okay, and we let it run on a slow computer, which only executes 10 million instructions, which is 10 to the power of 7. So that's basically 1,000 times slower than the computer A. Okay, and also we implement the algorithm with some high-level programming languages, which gives a very large C2. Okay, C2 is 50. So that's a very unfair comparison so far. Okay, now we will give the task, which is to sort 10 million numbers. Okay, 10 million is 10 to the power of 7. So let's compare it. Okay, let's do this interesting comparison. Let's see how much time the computer A will take, because we know the speed, we know the size of inputs. Okay, So the total number of instructions is the numerator here, which is 2 times 10 to the power 7. So this is the n. This is input of the size of the input, and raised to the power of 2, because that's determined by the formula of the insertion sort. Insertion sort assumes that we need to use C1 times n to the power of 2, right? N squared. And C1 is 2. So in this numerator, this is the total number of instructions to sort this input sequence. And we will use that to divide by the speed of computer A, because computer A runs 10 to the power of 10 instructions per second. So the result of this division would be 20,000 seconds, which is about 5 hours, more than 5 hours. Okay. And we will do the other algorithm using computer B. So remember, the formula for the merge sorts is different. Okay. For merge sorts, it's 50 times, so 50 is C2. C2 times n times logarithm of n. That is the formula for the merge sorts algorithm, and divided by the speed of computer B. Okay, so even though the computer B runs very slow, and even though the 50 is pretty large here, but since we have a logarithm here, the logarithm of 10 to the power of 7 is a pretty small number. Okay, the effect of taking a logarithm is powerful. It's so powerful. Okay, so that's the numerator becomes a very small number, and the total result will just be a few minutes, less than 20 minutes. There's a 100,000 seconds. So this is huge differences. And what brings the difference? Okay, it's the difference between the algorithms. Okay, even though computer B is a poor, is much slower computer, it has much worse hardware conditions, and the programming language is not fast either. But as long as the algorithm is a smart choice, the algorithm is properly chosen, then we'll have some huge advantage over a poor algorithms. Okay, and if you do that computation manually on your paper using a 100 million numbers as inputs, that'll be an even larger difference. Okay, so in a word, we can say that algorithm is also a technology in one sentence. So it's just like the computer hardware that people require to use nowadays to solve the problems efficiently and correctly. We not just need fancy hardwares, but also we need to use the algorithms that are correctly and efficiently designed. Okay, so the system performance depending on the efficiency of the algorithms as much as on choosing fast hardwares. Okay, I think once we finish these slides, we're pretty much done today. Okay, so almost all the other computer technologies are directly or indirectly dependent on algorithms, like computer architectures, graphical user interfaces, the windows we use, everything we see on the display. It basically depends on very fast rendering speed algorithms. Okay, like the object-oriented systems we use in Java, in Python, they all depends on very fast underlying implementations of the classes. like the fast wired wireless networks, that's even more dependent on fast graph-based algorithms. Okay. All right. So if we don't have good algorithms, most of the tasks we can still accomplish them. Okay. But with a good background in algorithms, we can do much more. Okay. And I think that's pretty much it of the introduction lecture today. And I would encourage you to go through the rest of the reviews for mathematical backgrounds yourself. And we will go through these mathematical backgrounds later, not later, but in the next slides, in the next Tuesday's class quickly, okay? So this will be the preparation we need to have before we entering the topics of the first algorithms we're gonna introduce. So you can think of this as some review work you need to do before the next lecture. And I will release the quiz questions. So there will be one syllabus quiz questions released later today. And after I uploaded the recorded videos to Canvas. Yeah, I will upload the slides as well. So they are not open yet. Yeah, okay.
Professor, I have a quick question.
Yeah.
In regards to the in regards to the quiz that's right now, what about us who are like still on the wait list trying to add the class? And you said you'll know later this week, like.
Yeah. So yeah. So that's a specific case, special case. I will cancel the deadlines for those not enrolled for now.
Okay.
Yeah.
And is it, you said it's like later this week, or is it most likely next week? We'll find out.
You mean the class size?
Yeah.
Oh,
That's what
yeah.
I mean.
So it should be after this week. It should be early next week.
Okay, thank you.
Mm-hmm. All right. Any other questions? No questions. Okay, good. So welcome everybody, and thanks for coming. And let's hope for a fresh start and a good semester, a good new year, and hope everybody enjoy your new year. And let me stop recording.
Wait, so is there a quiz after this, after right now?
There will be one quiz, but it will not be due today, but it will due in 2 days.
Okay, thank you.
Yeah.